Good afternoon. Welcome to the course Thermodynamics of Materials. We are into lecture number 95 and 96. We are discussing 4 issues that make thermodynamics a difficult subject for the students. And we are discussing reversible process, the second issue. And we could not complete yet, just little bit left. But before this, I would like to tell you that yes, yes. uh, this is the second point, and okay, okay. Hmm. This was discussed, but there is little bit of discussion still left with this second one. Okay, I mean this B, the second law criterion for equilibrium reversible process is this: how can a reversible process be carried out satisfying dGpt is 0? This we discussed. So today I'll tell you what whatever I missed last class. Last class I missed some points. So just maybe I'm keeping this. I'm keeping this because this is not yet over. Once it is over, then I'll go to the C and maybe then D, and still under this reversible process. That is the second issue. Second of the 4 issues. That is the subtopic. Okay, so this is reversible process. The second issue, and in the second issue, this is a B. So this I discussed, but first, before everything else, I should say one mistake, shocking mistake. So one mistake made in the last class. In the last class, what is that? That is I am showing you this drawing. That is reversible versus irreversible sketch. Irreversible sketch. I will give you for both expansion and compression. And compression. This expansion, actually everything was correct, but still for clarity I will give you actually in a more elegant manner. Okay, then let me draw this first. Maybe this side. Let us use this place. Sorry. This is P versus B diagram expansion. State 1 to state 2. State 2. This is reversible isothermal. System I am writing system 1 mole ideal gas. System 1 mole ideal gas. It's okay? Light is on. System 1 mole ideal gas. 1 mole of an ideal gas. This part was discussed perfectly well last day, but only thing is this clarity was little less. So today I want to this. This is the reversible. What is the name for this? 1A2. 1A2. Okay, very good. Reversible isothermal. Expansion. Expansion. What is this? This is P1, B1, T. This is P2, V2, T. This is reversible. What is the irreversible? What is the irreversible? Okay, irreversible. How many ways you can irreversibly carry out a process? Infinite. Infinite ways, because infinite values of finite driving force. Infinite. Infinitesimally small, unique. And that is for reversible process. And that is something tends to zero. Okay, any irreversible is what I said last day. Last day, this is straight one step. One step, I give a name to this. This actually 1B2. I'm writing this side. This side 1A2 is okay reversible. 1B2 irreversible. And what is this? This is here actually one step irreversible. One step. Actually, here it is better I write here one step. One step. What is the step? P1 directly to P2. Note somewhere here where you will write this. Right here. That is maybe here. P1 to one step. P1 to P2. Note here. P1 since expansion, so pressure is less. So P1 is greater than, there is a decrease in pressure and increase in volume. Okay, very good. Isothermal. So this is a 1B2. We dotted because it is passing through non-equilibrium state. That is the characteristic of irreversible process. And this is always passing through a continuum of equilibrium state, the reversible. Next, what I wanted to tell you last day, that since we cannot carry out reversible process, it is a mental process. So we will carry out irreversible process with a finite driving force, which is practical, which is feasible. So, but we try. What is the purpose of what is the okay importance of reversible isothermal? Why do we study at all? Why do we study? Because this gives sets actually I would say ideal standard. This is a standard. That is the maximum work done by the system. That is the standard reference ideal benchmark. So this, so compared to this, where it is, so we will try to get as close as possible to the reversible process. Any irreversible process, but still try to get as close as possible to reversible process, so that we get benefit out of this. The system work done by the system will be greater and greater as it close up to the reversible process. This is that. So, but I cannot show so many things. Only one thing. Another option I will show you. This is straight. Another option is I show you here. Oh, sorry, sir. Another one I'm writing here. I'm showing first. Aye, aye. Oh. If I talk too long, this, this is the next one. I'm giving name to one C. This would be D, obviously. D. This will be E. So what is the name? A1, A2 is the, this is, you can give a name somewhere. One, maybe here. Here is the 1, A2 is the reversible. 1, A2 is okay. 1, A2. Good. 1, A2 is okay. 1, B2 is also irreversible, but now it is what? Multi-step. Multi-step means two step here. It can be 3, 4, 5, 6, 7, 8. So 1 See this, and this pressure is, I am writing here, you will understand, this is somewhere between P1 and P2, interposed between P1 and P2, call it P3, call it P3. So what? First drop to P3, P3, so 1, C, D, D is the equilibrium state, remember. It hits the reversible curve and equilibrium. And then next, C, 1, C, D is the equilibrium state. Then next, so D to E to 2. So this is also irreversible. This is two steps. What are these? P1 to, first step is P1 to P3. P1 to P3, P3, okay, understand? P3. P1 to P3, then to P2. P1 to P3, P3 to P2. So we have actually number of steps, and it is now, this is now closer to this, closer to reversible process. So this I discussed, this is this one, okay. What else? Now this was discussed fully, and I will now show you the compression. That actually I made a mistake. So here you can see this work done is maximum, which are, what is work done? By this work done is, in the PV diagram, work done is area under the curve, okay. So area under the curve 1A2 is maximum, you can clearly see. For example, we compare this one, 1B2, what is the area? Only this much. I show you here, only, what is it? Oh, okay, only this much. This, okay? Yeah, this much. This is the under 1B2. And what is under 1A2, the reversible? This much plus the area enclosed here, so total area. So it is greater, it is maximum. But this one is greater. This is actually now, since closer to reversible process, it has actually work done more than this irreversible, but obviously less than reversible. Irreversible process cannot beat reversible process in terms of work done by system, because that is the maximum. But anyhow, it is better. It is okay, gives more work. So we will prefer this rather than this irreversible. This we will prefer, so that system does more work, efficiency better than this compared to this. So this is the best, but this is reversible. Okay, infinitesimally small driving force and impact. Okay, what I said this last day, it is actually, we cannot carry it out. Okay, and impracticable. Right, impracticable. So this part is last day I discussed, but today clearly I give the names only, 1, A, B, C, D, etc. Now compression. This I made a huge mistake. That mistake, one mistake is here. So please follow. Let me draw this. Last day, pressure against volume. Okay. So so this I am again drawing. This is drawing is 1, 2. What is this again? See, sorry, I am very sorry. 1 this side. This is a compression, and this moves in this direction. Name P1. Actually, you write here also. P1 is greater than P2. Achha, P1, what is this? 2 is what? P1, let me finish this. P1, T, P2, V2, T. The question is why reversible process is important. So this actually we are answering. Okay, this we discussed when we in the introduction, but today we are picking it up again to establish the point that why reversible process is okay, and is important. So this part actually was A. This is not the B actually. The A is what? Remember what is the A? A was, yes. The question I repeat this. A is this was. Why should we study the reversible process at all, while knowing it to be an impracticable process? While we know that it is an impracticable, why we carry out? The answers I have given, and this also I said of this number of steps. in that connection, these are not about this. This actually I discussed, but little bit left. That is not about this. This is about the first A. Why we carry out? Okay. Why should we study? Why should we study? Study reversible. Study the reversible. I am not writing, but you will get this from last day's lecture. Reversible process, etc., etc. Why should we at all? At all. Since this is etc., etc. impractical. In this context, this diagram I drew, I am correcting this today. And then I will pick up the remaining part of this discussion. Last day I discussed, I showed this, but still some discussion is left out, so that I have to fill in today. I will complete this. So complete this. This is one compression right here, P2 greater than P1, as you should. Compression. Yeah, shall I write this here also? What is this? Reversible isothermal compression. Work done, work done here, work done on the system by the surrounding. This I wrote. Okay, so I want to correct this. Oh, sorry. Actually, it is space I need. Actually, reversible isothermal expansion. I'll write somewhere. Let me complete the diagram first of all. It is okay. Is one, no doubt about this. One, and this is P1, V1 T, no problem. P2, V2 T. Sorry, P2, V2 T, that is no problem. But let me see. So reversible, how will go? This is reversible, an equilibrium process. So okay, this all lines are equilibrium. All lines represents the whole. This line represents the equilibrium states. Okay. Now to this irreversible. Irreversible goes straight. Sorry, it's so easy. Actually, what is this? B. B. So let me write this. This part is over. Let me write here. One. Oh, this is what I'm writing. This is two. This is two. One, two. One. And what's the name to this? Just give a name here. 1A2. 1A2 is what? Here, reversible. Reversible. Okay, isothermal compression. Then what is this? 1B2 irreversible, like this, irreversible. One step. What is the step? Tell me. P1 directly to P2. Compression P2 is greater. So this time we will consider work done on the system by the surrounding. So this is of the first irreversible one step, that can be now multi-step. Multi-step. So means say two steps. What it will be this like this. I say I go up to this point. System goes, then takes. So one I should write like this. One C. This is D, like this D, and then goes up again. It is equilibrium state. On the reversible path, equilibrium state. 1C D. D is a hot volume. This is hot volume. Actually, I am writing this a little below so that it is not comes here. Hot volume, hot pressure. It will be P1, P2, the intermediate. P3 I wrote. P3 I wrote with D. Here also same thing. P3. Then go up straight to this, and then take a turn. Shall I draw this? Hang on. Wait a bit. I'll try this. This is okay. This is okay. These are all okay now. This is 1B2. Now 1C. This is D. This is D. Then from D up, 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 hit, and this way 2. So this point is E, like E here, like E here, and E to 2 like this. So what is the name of this? 1. Tell me. 1C. 1C D D E 2. 1 to 2 always. 1 to 2. 1 to 2. 1 to 2. Initial final same. 1C D. It is irreversible two step. How will you write this? P1 to P3, P3 to P2. And here also write note this here. Here in this case, what it is this? What is P3? P1 is greater than P3, and P3 in turn is greater than P2. And as this I already wrote, P1, P2 is here. P1, P3, P2. P1, P3, P2. Okay. Here also similarly, P1 is less than P3, less than P2. As you see, P1 less than P2. Okay. P1 less than P3, P2. Okay. P2. Okay. Very good. So this is this is actually the relationship. So now you see, this is so first irreversible 1B2, 1B2. And second irreversible 1CDE2. It is closer to the reversible compression 1D2 or 1A2. I'm very sorry, 1A2. It can be 1D2 also, 1AD2, but 1A2 I have given the name. Sorry, 1A I have given the name 1A2. So this one 1CDE2 is closer to this. What is the impact on the work done on the system? Right here, work done on the system, done, compression. Okay, give this. What is reversible isothermal compression? Just this one, this curve. This curve. I don't write this. Well, this is, I don't have space here. So this is the part. This is the reversible isothermal expansion. Work done on the system by surrounding, by the surrounding. Surrounding is the external. By the surrounding. Okay, by the surrounding. Okay, and here work done by the system. This is expansion. Right here, expansion. Work done by the system on the surrounding. On the surrounding. Happy? Okay. So this part actually. So this is okay. This looks okay now. Okay, on D2, D is okay. Okay. This is 2. What is this? So you see. So in case of compression, the work to be done on the system by the surrounding, by the external device on the surrounding, on the system by the surrounding is minimum, because see, now today it will be correct. Area under this curve 1A2. This curve, sorry, this curve is this much, this much, this much, and see area under this first irreversible consider easy. This what is the area under the curve? Under this curve, the vertical line, no, this is full full area. This is greater than this area. So work done on the system will be greater in irreversible process. So this is greater than this. Reversible is the minimum, and as this 1 C D E2 is closer to reversible, here work done on the system will be less than what? Here work done will be less than this irreversible. This irreversible work done on the system is less than this, and least is reversible. This is less than this. So this is the getter. Here greatest. Then this. Then least is reversible as it should be. So in this case, work done on the system is minimum. Here work done by the system is maximum. So we will try utmost. What is this? Why do we study? So we try to develop a reversible process so that we develop an irreversible process which should be as close the reversible process as possible, as practicable. So here see, instead of one step, two step will be better. So if it is a compressor, so compressor we have to compressor has to do less work. In this case, so design purpose, this will be better than this. Of these two, this is not possible practicable. Of these two, this will be better because this since compression is a compressor we use, then in this case in the design we'll go by this irreversible process rather than this irreversible process, by taking the two step. If necessary, 3 step, 4 step, okay, and more and more, okay, less and less work done on the system, less work on the system, less work done on the system, and down on the system, the load on the compressor will be less and less as it gets closer and closer to reversible process. I think this what mistake I made. Just I am not going to draw this. I will show you. Instead of drawing this line, I very shocking that I irreversible 1B2. I was trying to draw in case of compression. This was perfectly okay. Compression I tried to draw this way. Just you can refer to that class. The lecture, I did this reverse mistake. I did this. I tried to, that's why actually I was not able to explain well. But actually it should be this irreversible. Thank you very much. So I have actually completed the backlog. I have completed the backlog and sorry. So now actually I tell you what, I will now take up the remaining part. Yes. So let me remove this. This is actually the pending, or say the mistakes actually took some time to rectify the mistake and to explain well these things. Okay. Regarding why should we study, but now I am removing this, and I have to remove this. Otherwise, I cannot discuss this. One point I almost completed, but 2 points are still left that I will explain. Then this B will be over. Then I will take up C and D. Then it will be reversible. The second issue will be over. Then I will take up the third issue and the fourth issue. So what is this? What one thing I want to tell you what. Yes, see this. Oh, I have removed this figure. No, it's okay. Okay. So in case you follow this, next I'm writing next means after last class. Next, you follow this diagram. Let me complete. P versus T phase diagram. P versus T. Recall this. This is the H2 phase diagram, and this is your H2 liquid, H2 vapor. Recall this. And what temperature I consider? H2, so let's recall H2 liquid to H2 vapor equilibrium. Recall the equilibrium. Recall the equilibrium. What is this equilibrium? In this context, I will show you something. I will show you something here. Today, what is this temperature? First of all, tell me. Tell me what temperature? Recall 342 T Kelvin, T atmosphere. What is it? 342 Kelvin. And what was the corresponding pressure? What was the corresponding pressure? It was 0.3 atmosphere. So this is 0.3. This is last days. Last days class, right? Last days class. Last days class. Happy? 0.3. So I just in this case, so this is the PT sketch, PT is PT. So I give you this. This point is what? I'm tell you first. This point is say E. I'm writing E. E for equilibrium. This point, water liquid and water vapor, H2O liquid, H2O vapor coexist. Perfect equilibrium. Perfect. I drew you the diagram for perfect equilibrium. Okay. So this 0.3, 0.3. Okay. This is so this is perfect equilibrium. So this is so E. I'm giving this. This is when this water liquid, water vapor at 0.3 atmosphere and 342 Kelvin, perfect equilibrium. No process, no reversible process even. So how to make reverse? Yes, let me write that. That will very good. Is point 342 Kelvin point E, right? Answer point E equilibrium. Equilibrium exists. And what a point is by oil point E is what you write nicely 342 Kelvin and 0.3 atmosphere. What we achieve here? This leads to equilibrium between H2O liquid and H2O vapor. Perfect equilibrium. Oh, right. You may write perfect equilibrium. This I showed you with the diagram, cylinder piston diagram. I showed you. I will not repeat this. No. Next is if you want to now reversibly evaporate liquid into vapor. This is the process. Next process under study. Reversibly vaporization. So what is this point? I cannot show infinitesimally displaced. Can I show heaven tends to 0? But anyhow, I try to put it as close so that you understand E prime. So E prime point E prime is what? Is infinitesimally displaced. I'm writing you understand. 342 unchanged. 342 Kelvin unchanged. That is on that temperature. At that temperature, I'm drawing this. This is what not anymore 0.3, just little drop. 0.3 Kelvin minus D. I cannot show, but I have to, somehow I have to show this, or mentally you do minus D. It is what? Reversible evaporation of H2O liquid into H2O vapor. Happy? And you see, this is the vapor phase, stable phase. This point and this point, this zone is liquid water stable phase, and this point is coexistence. Both are stable. This is the phase diagram. This is actually a phase diagram of water. Single component phase diagram. This phase equilibrium we discuss this. So next is suppose here consider this point E double. This will be then guess point E double prime is what? How will you express this here in this manner? Temperature remaining same. Temperature we don't change. We work on the pressure side. 0.3 minus finitely smaller than 0.3. Finitely E prime. So what you call this? This is also evaporation. See H2 vapor irreversible. irreversible evaporation of same thing, right? Of H2O liquid into H2O vapor. So vapor will be stable in this zone. Okay, this is a phase diagram. So caption may be given here. Figure, call it figure 1C because for figure 1A, 1B I gave. Last perfect equilibrium I gave, and then reversible I showed. Then irreversible also I mentioned or showed, whatever. But figure, so write this. This name of this figure is 1C. Now we are discussing this. This is over. Remove this. This is completely over. B just a concluding part, and of this is one and another one coming. So let me finish this figure once it is over in a sense, but let me give the caption. Comparison of the, this is the caption, comparison of the comparison of the equilibrium state, comparison of the equilibrium state for which one, H2O liquid and H2O vapor. This equilibrium equilibrium state, reversible evaporation, comma, reversible evaporation is a reversible evaporation, reversible evaporation, okay, and irreversible evaporation. I can remove this now, this now unnecessary, and unnecessary, and irreversible evaporation. Evaporation and evaporation with the help of with the help of with the help of PT diagram, PT phase diagram of H2O, PT diagram of H2O. That is the phase diagram. That is the phase diagram of H2O. And H2O, this one component we have not shown here solid. Ice we have not shown here. So liquid water and vapor water, because that is pertinent to our discussion. So this is over. So last, still another point, the last point about this B. Last point, you can see, note the difference between I tell you what, note the difference between, this will also actually remove your confusion about reversible process. See, note the difference between, note the difference between the reversible isothermal expansion, of n moles of gas, ideal gas, of n moles of ideal gas, n moles of ideal gas from state 1, P1 V1 T to state 2 P2 V2 T, P2 is expansion, P2 is less than P1, and the reversible and between this and what? Reversible, reversible evaporation of a finite quantity and reversible evaporation of a finite quantity delta N may be of a finite quantity of H2O liquid and you have a finite quantity of H2O liquid, okay, into H2 vapor. I give you with the figure. Recall the figure, corresponding figures. First one, cylinder piston arrangement. This is state 1. State 1. What is this? P1, V1, T, thermostat. Just quickly, this is repetition. Thermostat. What is this pressure? P1 initially, say N moles ideal gas system. This system, what is the pressure? External pressure surrounding. External means surrounding. P1 and thermostat is the surrounding. This, so what is the temperature? System gets the same temperature as the surrounding T. This is the initial. Now we want to at state 2 is what? This is the goal. P2, sorry, P2 V2 T. P2 V2 T. How we proceed here? Just follow. Reversible. I have written in here reversible. Reversible. Underline reversible. So how will you get? P1 next is P1 minus dP. Then this is P1 minus dP. Then P1 minus 2 dP. Then this way, P last part 1 P2 plus dP, and the last P2. This is the journey reversible dP 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 dP. Okay. So many pressures we apply. First P1, then to upset the equilibrium. Otherwise there won't be any process. P1 minus dP. Then P1 minus 2 dP. This we discussed. The reversible process. Nothing. But this is, note that there are actually infinite number, I should say that, okay, or say numerous pressure applied, okay. In contrast, this is the this is in contrast. I will write you, okay. In contrast, what is the water liquid? Water figure is what? Tell me. This is your water liquid. This is the water vapor. Recall last day water vapor, okay. Water vapor. So this is H2O vapor. This is H2O liquid. Evaporation. So what is the vapor pressure is 0.3 atmosphere. Remember that value I consider, and there is a thermostat. Temperature is 2. Thermostat I am not showing here. Okay, you know this. 342 Kelvin. And when it is 0.3, you just put 0.3 atmosphere load from the external. External pressure, internal pressure 0.3, balance, perfect equilibrium. E, point E, perfect equilibrium. This I said. But how do you carry out this finite amount or dn moles of water? You did something. What you did? 0.3 minus, unless you upset the reversible process will not take place, but upset by an infinitesimal pressure dp, this is sustained or maintained. Sustained. Suppose you want to a finite moles, let's say dn moles, then dn. You have not changed. You have not changed. dn. So finite quantity, say delta n moles, like say 1 mole, like say 2 moles of liquid water will be evaporated. The entire water will be evaporated. By keeping at this value sustained and not changed anymore. Here what? This is P1 minus dp, then P1 minus 2 dp, P1 minus 3 dp, P1 minus 4 dp, and final last but one P2, last but one or last but two is P2 plus 2 dp, then P2 plus dp, then P2. So many actually changes. Here only one. This is reversible. This is reversible. This is reversible. Both are reversible. This is reversible, and this is also reversible. Reversible evaporation, reversible. Here also integration finite moles. Here it is actually this moles actually are giving n moles. So you have finite change. Here finite change 1 to 2 state wise 1 to 2 finite change, and finite number of moles evaporated. So both are finite quantity dealing with finite quantity, and both are reversible. The difference, big difference, is this conceptually. Here you don't write 0.3 minus 2 dp. Useless, meaningless. 0.3 minus dp. No, needed. This is enough. 0.3 minus dp is good enough to make the imbalance, and it is continue. You see, once it is actually evaporated and making it 0.3, then the sustained 0.3 minus dp makes the pressure 0.3 minus dp, and again then further evaporation to make it 0.3. So once it is chemically trying to make 0.3, and this mechanically it is trying to make 0.3 minus dp. Surrounding is trying to make it 0.3 minus dp, and chemically equilibrium tries this. This conflict makes the process going. Finite quantity, any amount of liquid water can be converted into vapor. So this is a reversible approach. This is a reversible. So this I am going to tell you. So I showed you everything. Let me write a few lines here. So will you please draw a border here? Now, so H2 liquid into H2 vapor. Okay, just few more lines. H2 liquid into H2 vapor. Okay. In the former case, underline this underline reversible, right? In the former case means this case, is it? First one. In the former case, in the initial starting pressure is the starting pressure. Sorry. The starting pressure is P1. This is the system pressure as well as the external applied. Okay. This. So this is so opposing that. Opposing, I said, external is two types: imposed or opposing. So this is actually opposing. So, but against this opposition, system does work. So don't worry about this point. Case the starting pressure is P1, and the subsequent pressure is P1, and the subsequent pressures and the subsequent pressures are tell me P1 minus dp. Sorry, P1 minus 2 dp. Oh, sorry, P1 minus dp, P1 minus 2 dp, P1 minus 3 dp, etc. etc. until P2 plus dp to P2 okay. This to create to cause the expansion cause the expansion of the finite number of moles of the gas, of the finite number of moles of the gas. What is that gas? Finite moles. I wrote n moles. And number of moles of the gas. This is about this one. Okay, of the gas. Okay, from volume V1. Acha, right. Complete this from volume V1 and corresponding pressure is P1. Volume V1 to volume and corresponding pressure is P2. Volume V1 and volume 1 right here, pressure P1. Okay, other looks bad. Pressure P1. Pressure P1 to volume V2, pressure P2. This all actually about this. In the later case, this is in the former case. In the later case, I write here. In the later case, I give a star mark here. In the later case, just let me write here. This is not needed anymore. I think, or no, this is not needed. I write here. This helps me. Right here. In the later case, star. In the later case, what happens? The reversible evaporation. The reversible in this case, former case, later, the reversible evaporation. The reversible evaporation of a finite quantity. What is that? Remember, finite quantity is delta n, dn, integration dn is delta n. Finite quantity, delta n moles, delta n moles of H2O liquid, is carried out keeping the pressure, keeping the external pressure, keeping the pressure fixed. This pressure, so the external pressure, this pressure, the external pressure fixed at, and when the external is imposing on the system, that system has to be 0.3 minus dP. But again, there is actually chemical equilibrium requires 0.3, so there is actually imbalance, chemical equilibrium upset, so evaporation takes place. This I discussed. Pressure fixed at, let me write the pressure fixed at what value? 0.3 minus dP, or rather you write here, why you write this? Fixed at P1 minus dP, okay, 0.3 minus dP I have written. So the pressure fixed at, give me the pressure fixed at, I am writing P1 minus dP, sorry, P1 minus dP, P1 minus dP, that is 0.3 minus dP, 0.3 minus dP 0.3 minus dp is 0.3 minus dp. This is P1. If it is P1, P1 dp only. Just this fixed at this. No more P1 minus 2 dp, P1 minus 3 dp. No, unlike this, different. So this, reversible does not. Then the question may be asked that, sir, why we have actually in the reversible this is number of dp's, but here only once. Why not here? Not needed. That is not needed. That's an impossible thing. Okay. If it is 0.3 minus delta p, then it will not be reversible anymore. dp on many dp's. Okay. Number of dp's integrated over integrated gives us delta p. The moment it is delta p, this is no more reversible. We are discussing reversible. So, moreover, dp actually in irreversible we write here straightforward 0.3 minus delta p. So this is 0.3 minus this difference 0.3 minus dp or p1 minus dp. Here this series each point reversible process. Each point continuum of equilibrium state. So that's why. So this is the main difference. 0.3 minus dp at 0.3%. P1 minus dp only. Like I'm writing, no other pressures like what? P1 minus 2 dp, P1 minus 3 dp, etc., 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 used. No other this used. This only this for the entire duration of the process. Used for the entire duration of the process. For the entire duration of the process. And just draw a line here. So this part is discussion is completed, and all associated thing, all ramifications, all are discussed here. So now we'll take up C. Okay, this is over. So let me take up C. That is reversible issue is second issue is reversible process under which C now. What is C? Question answer. So question. What is the question? Question is what? Yes. Is it possible? Question. Is it? I'll remove this figure. Okay, I remove this everything. Let me write the question first. Is it possible to carry out a spontaneous reaction like metal solid plus oxygen gas goes to MO2 solid? Reversibly? This is the question. We have shown H2O liquid into H2O vapor reversibly. This is a chemical reaction. I said phase transformation is a chemical reaction. This reaction. But question remains that, okay, well, fine, it may be possible with H2O liquid evaporation. But is it possible for such reaction? Can it be carried out irreversibly? We carry out irreversibly as metal and oxygen oxidizes irreversibly, spontaneously. So is it possible? No, so this is the next. So remove all this. This is the C. We will actually complete this. Let us see how much time it takes. That's answer. What is the answer? Answer is very much possible. Answer is, actually, wait a bit, I have to change this. Answer is very much possible. And you will be surprised to hear that this will be carried out in the same manner as H2 liquid, H2 vapor evaporation. Exactly same manner. Only just find out the equilibrium value. That delta G0 business, equilibrium constant, then next. See, because remember, anytime reversible process you want to carry out, initially it should be at equilibrium. Perfect equilibrium, then disturb by an infinitesimal amount. This is the recipe. This is the recipe. Anytime carry out reversible process, how? Initial state is equilibrium, perfect equilibrium. Then slightly displaced, means infinitesimally small. Infinitesimally displaced, then it will be reversible process. And finally displaced, irreversible process. Start. Very much possible. What it is said. Let us consider the reaction. Consider the reaction. Reaction M plus O2. I am not writing. Okay, M plus O2 is MO2 in short. Okay, M solid, etc. I don't write. Okay, M solid, right? Reaction M solid plus O2 gas goes to MO2 solid. Here is a reaction taking place at temperature T. Taking place at temperature T. At temperature T is 1000 Kelvin. 1000 Kelvin, for which the equilibrium PO2 is 0.05 atmosphere. Say to obtain from, how will you get this value? Obtain from famous delta G0 is minus RT ln K is K is here 1 by PO2, so it becomes RT ln PO2. Okay, this. So from this delta G0 is known from data book, known data book, from data book. So you get PO2, equilibrium PO2. Very good. If you got this, very good. Is RT ln PO2 equilibrium? I have written here. RT ln PO2 equilibrium. Happy? This is very good. So the the process arrangement very much like that of well, the process arrangement, no problem. Very much like that of H2 liquid is H2 vapor, just discussed. Exactly same. H2 liquid is H2 vapor. Reaction H2 liquid. This is the phase transformation. This is the reaction in figure 1. Remember, figure 1, actually figure 1a, figure 1b, that is the arrangement I showed. Okay, figure 1, figure b. So that in figure 1, very much like that of this reaction in figure 1 is shown in figure 2 here. Is figure 2 here. Shown in figure 2 here. Okay, I draw this diagram, then that will be very easy for us to discuss. Okay, I am drawing the diagram first, initial one. Very easy, same way. Only you have metal, oxygen, metal oxide. Okay, so again, thermostat. Thermostat. T is 1000 Kelvin. What you have taken here? Metal solid, metal solid, metal oxide solid, metal oxide solid, and oxygen gas. What is the pressure of this oxygen? And here it is P. P is what? PO2. What is that value? Oxygen value is what? PO2 is what? PO2 is what? 0.5. You see here 0.05. Oxygen PO2. Don't have to write this. I am writing here 0.05 atmosphere. So here also PO2 is what? 0.05 atmosphere. This is the initial state. What is this state? You will call this? This metal and metal oxide with an equilibrium value of PO2. What will happen? What will happen? This is 0.05. So that means this is actually perfectly with this external pressure same. And this metal and metal oxide is, this value is the equilibrium value. So the reaction is in equilibrium. This is perfect equilibrium. So in initial state, this is the perfect equilibrium. Means no process may occur. No process, perfect equilibrium. No, even reversible process won't occur. To make a reversible process occur, small imbalance, infinitesimally small change required. What it will do this similarly, just this is the first step, nothing will happen. Forever remain here. Although we say reversible process is an equilibrium process, but no, this perfect equilibrium means exactly equilibrium. Reversible process is slightly displaced from equilibrium, infinitesimally displaced from equilibrium. Essentially equilibrium. No doubt, but we have to understand that. So what we will do to carry out reversibly? Here for oxidation you know very well what to do. Pressure should be greater than equilibrium pressure so that reaction occurs in the forward direction, forming metal oxide from metal. So next figure would be what? The perfect. Next figure you repeat this diagram. First you draw the diagram. So same. So this goes to this I am writing. This is the reversible oxidation I am writing. Reversible oxidation, just short I am writing, but I will give the caption of this, okay, at the end. Sorry, below it. So this is what shall I write? Write similarly metal solid. You have metal oxide. You have as before metal oxide is okay. Metal oxide solid. You have an oxygen gas. You have but this is subjected to not 0.05. What is the P? P will be slightly 0.05. Now plus or minus dP, plus or minus dP. I am writing plus dP. Can we challenge this? Yeah, it should be more than 0.02. Q less than K, delta G negative. Remember all those things? So when it is greater than equilibrium, they move in this direction. So this is plus dP. Okay. So this is that. Again thermostat. Thermostat you can show always. Thermostat. Temperature is 1000 Kelvin. What else? What else? Nothing else. Okay. When this is 0.05 dP, inside is also 0.05 dP. Okay. But it did not allow this because equilibrium requires 0.05. So some oxygen should be decreased from 0.05 plus dP to 0.05 because 0.05 is the equilibrium value. Exact. So oxygen will be dn moles of oxygen will react out, forming metal dioxide and reacting with N, forming metal dioxide, dn moles. And see, it is sustained right there, again sustained. Again, then so once it dn moles goes, it becomes 0.05 oxygen is, some oxygen is consumed, dn moles consumed, then it is back to what value, so that it come back to 0.05, but again sustained. So again the imbalance. So again actually it will be squeezed to 0.05 plus dP, again the reaction. So what should I write here? Oxygen gas also this. So oxygen gas actually moving this between 0.05 dP, then 0.05, then 0.05 plus dP, then 0.05 inside. So because of this sustain. It's done. Sustain. What else I will write here? Okay. So this is the final state. I will write final state, or what should I write other? So in the process, what will happen? You can write one thing. So finite. So this is dn moles oxygen, dn moles. When oxygen, dn moles of oxygen, dn moles of oxygen, dn moles of oxygen. So delta n, a finite number of moles of oxygen will be oxidized, will be removed, and causing oxidation of metal into metal dioxide. Reaction moves in the forward direction means metal will be removed, oxygen will be removed. Okay, that means volume will be actually squeezed, actually, or reduced to maintain the pressure. So this part I am not discussing. I am discussing is this. What is this? Metal solid will be what? Suppose finite moles of oxygen has reacted, then it will carry, it will bring. It will react. Okay, it will remove along with it metal solid and forming the corresponding amount of corresponding moles of MO2. So what you can write in this process? Metal solid will decrease. Okay, moles of metal solid decreases. Moles of, because reaction, you want the reaction, so this will decrease and this will increase. Oxygen will decrease. Oxygen decrease, but then volume is correspondingly decreasing, making the pressure at this value of 0.05 and switching between 0.05 and 0.05 plus dP. Moles of M solid what? Decrease, and moles of MO2 solid increase. This should be noted at the same time. Okay, moles of MO2 solid increase, decreases, decrease. What else you want to maintain here? Okay, nothing. Okay, this is. The caption is this caption I am giving you. Figure. What is the name of this figure? Figure I have said. What figure I have said here? Figure 2. So call it figure 2. Give the caption. Caption is what this? This is actually reversible. Let us write full. Reversible oxidation of dn moles of dn mole or delta n moles of metal solid into metal oxide solid is 2. It is very 2. Oxidation of these two metal oxide. Why dn and delta n? So dn start, then it continues, then it becomes delta n. dn integration of dn is so this. Okay, I have to solve it under P external. P external is what? This one, surroundings. P external is what? Is 0.05 plus dp atmosphere. This atmosphere and temperature is what? So that's it. That's it means this part is diagram is over. This is the caption. So dn possible dn if you stop. How you stop this process? Suppose it has started. Okay, so consider. Suppose 3 moles of metal solid has have reacted, and you are kind of okay, happy, satisfied, and you don't know you don't need any more oxidation, any further oxidation. Okay, you want to stop this. You want to save the remaining metal, and you want to close this reaction. How will you close it? These oxidations under this sustained continuously oxidation will take place. Metal will oxidize into metal dioxide. Suppose you want to stop this in the middle. Suppose 3 moles have oxidized, you don't want any more oxidation. Now what you will do? What is the easy way to do? Stop this in every case. In previous cases also. How to stop this? Just put back the value of 0.05. Remove dp. Just make it 0.05 back to 0.05. Then this condition stops 0.05 outside, inside, and equilibrium value. Chemical equilibrium, mechanical equilibrium. So full this perfect equilibrium. That means this condition is returned, is regained. If you just remove this. So you can stop this after any amount of moles have any moles of any amount of metal solid metal have any metal any amount of metal has oxidized, has been transformed into metal oxide. So after any extent, so this up to you. You can stop this. This is how you can stop. Just remove this driving force. And remember, with this, so you have understood both is possible. dn possible, dn to begin with, and then it will be integration of dn is delta n equal possible. If you want to carry out irreversibly, that I will write you irreversibly. Suppose this is reversible. Irreversibly, you know very well. Is what? This will be 0.05 plus delta p, finite driving force. 0.05 plus and finite driving force. So that will be irreversible oxidation. So let us point out this point and look at this case. So let us see. So figure 2. Okay. So in figure 2. Comment. 2 comments I am making. What I said I am writing in the comment. Comment 1. Comments 1 is what? dn, not only dn or delta n. dn mole. Always remember, delta finite change can be made reversibly, not not d only. Not d is actually okay. D is limited to reversible, as I have said. Or for reversible means d change only, dn change, finite change. See, Ideal gas expansion, state 1 to state 2, P1 V1T to P2 V2T, finite. So careful. So so comment 1 is dn mole or dn moles, delta n moles. Moles of M can be reversibly oxidized. Reversibly oxidized to MO2 by maintaining by maintaining the T at 1000 Kelvin and P pressure at maintaining T and P pressure at, pressure means this pressure, P at, tell me, 0.05 plus dP atmosphere. So this is one. What is the purpose of this? So that your mind, you should not have any mental block. Reversible does not mean dn only. Finite. Reversible 1 to 2, finite. Same moment you remember, reversible expansion I drew 1 to 2, finite. dB started with the dW, etc., etc. Work done. dQ, du, dW, etc. You remember this? Very good. This actually you knew perhaps, but I highlighted this point. Okay. On the other hand, on the other hand, if the preceding oxidation, oxidation is carried out, is to be carried out irreversibly, the external pressure must be external pressure must be what? Tell me, 0.05, that is plus finite driving force, 0.05 plus delta P atmosphere, in order to ensure a finite driving force, delta P. What is the driving force? 0.0 plus delta P minus 0.05 delta P. And here what is the driving force? 0.0 plus dP minus 0.05 dP. dP is the driving force, delta finite driving force, infinitesimally small driving force as is required for a reversible one. This is for irreversible. Finite driving force, keeping the temperature constant at constant at 1000 Kelvin. So same, just make it 0.05 plus delta P irreversible. Again, any quantity you want. And if you want to stop, suppress, okay, don't want any more oxidation, return it to this value. 0.05 plus delta P, say suppose, back to 0.05. Stop. Okay, next point, 2 comment, second comment. If the external pressure, this is important, if the external pressure, this question you could have asked, if the external pressure is made instead of 0.05 plus dp, if we make it 0.05 minus dp, then also, okay, okay, the infinitesimally small change is made 0.05 minus dp atmosphere, what will happen? Yes, then if pressure is equilibrium value is 0.05, less than that, more than that, this way, greater than this way, less than this, the reverse way. Metal oxide will dissociate into metal. So this is the message here. Is 0.05 minus dp atmosphere for reversible process, or 0.05 minus delta p atmosphere for irreversible process. Irreversible reaction, process means reaction, reversible, irreversible process. What will happen? The reaction will as I told, more than equilibrium value, this way, Q less than K. Follow that principle. In this direction, when it is plus, delta G is negative. When it is minus, delta G is negative in this direction. So the reaction will occur in the reverse direction. In the reverse direction, that is reverse direction. I am giving star here. Star here. I am writing here. I am removing these lines, the stop lines. Just this star here. That is MO2 solid. Oh, this reaction distribution here I wrote is removed here. That is okay. M plus O2 is MO2. Reverse direction means this way. That is MO2 solid will be reduced to this over. Actually, you could have asked this question at the beginning. You don't want oxidation. You have taken these three, MO2 oxygen, you want to reduce MO2. Then what it will do? First get the equilibrium value, starting point, equilibrium in the pressure here same. Then you actually upset the equilibrium, reversibly or irreversibly in this. Another thing I just mention you in passing, that you can work this side also, temperature side also. Then don't change here. Then you don't change here. Temperature side, if you want to oxidize it, it will be, I tell you, I know that it is exothermic reaction, so temperature should be, when temperature decreases, this will be the forward direction. This is exothermic reaction. So what you will do there, you don't change this time. Not work on the pressure, but on the temperature. That both are surroundings. Okay, temperature is what? This one, what is what? 1000 K. This will be what? 1000 minus dt, reversible. So again, the same thing will happen. Minus dt, temperature decreases, so oxidation. Same thing. And if you want to reverse it, dissociate metal oxide into metal, 1000 K plus dt, then this is removed in this direction. That is possible also. And this is all dt is for reversible, and for delta t, 1000 plus delta t, plus delta t will be for irreversible one. Okay, then this. Okay, always dt and delta t. But if you want to get this, your intention is to dissociate MO2, reduce MO2, then you have to follow this reversible and irreversible. So many possibilities are there. So you can very easily understand once you follow the basic things. Okay, and is okay, concept is clear, then no problem. Thank you. With this, actually, I have drawn the line here. So second is over. So now I'll take up the third one. No, I'm very sorry. Second reversible process is not yet over. Sorry, it is actually, it was C there. You have to remember well, it was C. I'm very sorry. This is not yet over. Sorry, it is not yet over. So remove this. Remove this. It is not yet over. So maintain this. What you will do this? This is C is over. This is a C. Next is D. Recall this. It was C actually. Reversible process. D now. Under this, what is D? This is next question answer session. Okay, question answer. How is a chemical reaction question? Students ask question. How is a chemical reaction carried out in an electrochemical cell? Electrochemical cell reversibly carried. Oh, sorry, very important. I missed reversibly. All about reversible process. How a chemical reaction. So we have seen a chemical reaction is reversibly carried out, but it is in a cell, electrochemical cell. How electrochemically? This is the question. Answer. To answer this question, let us consider the following. Aqueous phase reaction. Aqueous phase reaction. What is the reaction? Zinc solid plus copper sulfate. Aqueous solution but saturated. Saturated, you know what is saturated? Activity is 1. Copper sulfate saturated means saturated copper sulfate means you have this solution is completely saturated. If you add more, copper sulfate solid will settle at the bottom, will be separated. So that aqueous saturated goes to what? Zinc sulfate, that is also aqueous saturated plus copper solid means pure solid, zinc pure solid. Okay, happy solid. Okay, call this very important reaction 1. Call this reaction 1. The theoretical EMF, let us go on. The theoretical EMF EMF, which is E, of the electrochemical cell based on this reaction, this aqueous phase reaction, based on this reaction is found to be we all know this value is found to be 1.1 volt. Using the relation, there is a nice relation using the relation, thermodynamic relation is what? Using the relation delta G is delta G0 here. Why? Everything is standard state. Okay, since reactant and products are at standard state, are at standard states, standard states. For example, copper sulfate, aqueous saturated, and zinc sulfate aqueous saturated. Time
1 hour 37 minutes.
And zinc sulfate aqueous saturated. These are all have unit activity, as I said, are at unit activity, as good as solid. Saturated means if we add a little or a little more of this, they will be separated as solid because you cannot take up anymore. It is already saturated. So solid copper sulfate will settle. Means and solid copper sulfate is pure unit activity. So the solution also unit activity. Saturated solution are at unit activity. Quickly are at unit activity. I am just each are unit activity because they are saturated, and both zinc solid and copper solid are pure state, are at are pure solids. So here we are getting all activities on means standard state. Okay, so standard state activities all one. So this is one pure solids standard state. So this. So what it will be? So continue, delta G0 is minus NFE0 is here. Okay, minus NAP first. Delta G is minus NAP and delta G0 is minus NAP0. So all are equal. Okay. So since because delta G0 is negative, for this reaction delta G0 is negative, because delta G0 is negative, E0 must be minus. Minus is there. If it is negative, delta G0 is negative, means E0 is positive, and what value it is? 1.1 volt. Okay, as we have already seen. Here you may note this, noting N is here 2. Number of electrons they say, but I would write possible number of electrons in the half cell reactions. But you may write number of, alternatively, gram equivalent per gram mole. That is your valency or number of electrons. So per gram mole, how many gram equivalents are there? Okay, that is the valency. Is to number of gram moles. This is N, if you know, 96500 coulomb. Coulomb spelling maybe to this I have to coulomb, you know. What is this coulomb? Spelling is coulomb per gram equivalent per volt. Noting this, and you get E0, find this E0 in volt, okay? E0 positive 1.4 volt. Now this okay over. Now to carry out the reaction 1, now to carry out reaction 1, reaction 1, electrochemically, in a reversible manner. Now come. Remember, question is reversible. The whole discussion on reversible. The last point. Second issue, reversible process. Last point. Electrochemically, in a reversible manner, in a reversible manner, an external opposing EMF and external, see, similar things coming, an external opposing EMF. What is that opposing? 1.1 is the theoretical minus D, a little bit smaller, infinitesimally smaller than 1.8. So that if you apply exactly 1.1, then there will be no reaction will occur. I'll discuss. Okay. 1 point, it will be in equilibrium state. Okay. I'll discuss this. This point is little tricky. 1.1 minus D opposite volt. D volt is to be imposed. Imposed as shown in figure 3. As shown in figure 3. Now I will draw the figure, this arrangement. Suppose you actually have a little bit below straight line. You have a division here. You have here this is, and this is thermostated. This is thermostat. Actually, this value is actually after 298 Kelvin. 298 Kelvin thermostat. That is there. This is what? Zinc sulfate, and you are dipped a zinc rod. This is the zinc rod anode, and this side is what? You have just to contrast. This side is copper sulfate solution. Right, again saturated. Maintain this. This is zinc sulfate. solution aqueous, saturated, zinc rod, and you dip here. This is copper rod, cathode, and connect this with an external EMF. What is this? Here you write opposing EMF. Sorry, this is right, opposing EMF. This you have to EMF. This theoretical value is 1.1, so you actually write shall I give a star here? I don't have space here. You please write here. Opposing EMF, opposing EMF, you know what it is? It is what it is 1.1 minus D to be reversible. 1.1 minus D, so the reaction can move in this direction. Minus D volt for reversible operation, for reversible process, for reversible operation. And you can say yourself, and opposing EMF 1.1, tell me, minus delta E. Delta E can be 0.1, 0.2, 0.3, 0.4. D something tending to 0. Volt for irreversible operation. That's it. This is opposing. So this is the what else I should write? Copper sulfate saturated. Everything is electron flow. Zinc sulfate. Here, direction of electron flow is this, and will come this way. Electron is a negative current, and positive current in the opposite direction. So this is the whole about this. Now I tell you what. Okay. Now I tell. See. Let us go ahead. Let us write this figure. Caption is what? Figure. I've written figure 2 somewhere. Figure 2, figure 2, figure 3. This is figure 3. Figure 3 is just reversible, irreversible, reversible, irreversible, operation of chemical reaction, operation of chemical reaction. So in another way, I am carrying out reversible process electrochemically. In chemical reaction 1, you know, this one. What is the one? This this one, this one in the forward direction, in the
1 hour 49 minutes.
49 minutes. In the forward direction, I'll stop in 2 minutes. In the forward direction, what is the forward direction? Zinc plus copper sulfate, zinc solid plus copper sulfate goes to zinc sulfate solution plus copper solid in an electrochemical cell. An electrochemical cell. So actually, I tell you, Just two things. Note here two lines. Acha. What is the driving force? Driving force for the reversible is what? So note you understand this D exactly this D. How it is? Note the driving force for the reversible process is what? You can guess it is 1.1 minus 1.1 minus D. This difference is the D is D volt which is an infinitesimal quantity which is an infinitesimal quantity. D means D tends to 0, infinitesimal quantity satisfying the infinitesimally small driving force, that is the requirement of reversible process. So that is satisfying the requirement of a requirement of a reversible process of a reversible process of a reversible process of a reversible process. So it is satisfied, and the driving force for the irreversible process is for the irreversible process. Tell me, for the irreversible process is similarly do what is this driving force here? 1.1 sorry 1.1 minus 1.1 minus delta E gives you delta E volt, which is a finite quantity. Finite quantity. Acha, good, thank you. Which finite quantity and finite driving force. That is the requirement of irreversible process. Irreversible process, finite driving force delta E, and D for reversible process, that is the requirement infinitesimally small driving force. So both are satisfied. So particularly we are concentrating on reversible process. So what is the driving force? D infinitesimally small. So that criterion is satisfied. So we are also satisfied that this is actually reversible cell. But we have not completed yet. Not completed yet. Next class. So we will pick up this next class and complete this. Okay. Thank you very much for your interest and attention and your okay, your devotion and all these things, positive things. Okay, and your patience. So thank you very much. With this, we have actually completed today's class, and I will be off now. So we will meet next class, and till then, okay, bye. Okay, we complete this. Okay, bye. Thank you very much. See you later. Bye.